jet because it alone uses deuterium and tritium as fuel. But there is no such thing as a free lunch in a fusion plasma. Ironically, this success in heating the plasma has a downside relating to its purity.
Now, the impurities come through two different mechanisms in a tokamak. The first one is because fusion reactions produce alpha particles, and after the alpha particles have collided several times with the plasma to transfer the energy, they will lose their energy and sort of slow down and remain in the plasma and dilute the deuterium-tritium fuel, which is necessary for the fusion reactions. Unfortunately, you cannot get rid of all the impurities that you produce, which is what ideally one would like to do. So what we have to do is to try and keep impurity production to its absolute minimum. And that's why JET operates with a diverter as well as other tokamaks in the world. And the main idea behind the diverter concept is to try and separate the core plasma, which is hot, from the edge, which is cold.
This outer region is where the alpha particle waste, together with impurities knocked off the vessel walls, congregate. So how is this separated off?
This separation is achieved by creating a magnetic separatrix inside the vessel, just by having additional magnetic coils, which actually diverts the edge plasma from the core and sort of flushes it away from it through a separate chamber that we call the diverter, which is placed at the bottom of the machine.
Each new shape of diverter was tested in a full fusion experiment. A key run took place in 1996.
All ready? Beams ready?
Each plasma lasts for less than a minute. The leaders of each session must adjust the magnetic fields and the injection of new plasma in the search for improvement. It's a trip into the unknown.
So now we're in the last 30 seconds of countdown. Gosh, that's quite a pulse, isn't it?
The results of every run are analysed and stored. Each team looks for clues in its own apparatus as to how the plasma is behaving with the new diverter.
And which is the bigger anyway? The 1 to 10 is larger, horizontal, that's the way around it was.
The way a plasma dances to the orchestrating magnetic fields is one of the key pieces of physics now being unravelled with the diverter present. It will dictate the success of future machines.
The plasma, this hot gas, which we call plasma, is a bit like an unruly crowd. It tends to go where you don't want it to go in very sudden fashion. So much of our research has been to study the condition under which the plasma is stable. JET has demonstrated, for instance, that it's possible to have very good confinement, very good insulation, both at the edge of the plasma and in the plasma core. And that has allowed JET to reach record fusion performance.
As the power was increased, JET scientists and engineers waited for the signs that the plasma was producing a new record in controlled fusion energy. By late 1997, a pulse of more than 16 megawatts of fusion power had been achieved for the first time in a controlled fusion experiment. The aim now is to scale up fusion experiments to reach the all-important stage where the plasma can be heated sufficiently by its own alpha particles so that the temperature is maintained with little extra heating. So how has JET pointed the way? Progress has been made at JET on all three factors needed in the so-called triple product: the density, confinement time, and the temperature. Each has been achieved separately to a level necessary for a reactor. That is, good enough density, a temperature of over 300 million degrees exploiting JET's powerful heating systems, and a confinement time of more than 1 second, possible through JET's size and operating concepts. A clue to the nature of the next challenge, combining the three conditions, comes from the secrets which a plasma is still revealing on its crowd-like behaviour.
Plasmas have similar characteristics. they tend to flip into a mode or another mode. And this has been one of the most exciting things for a physicist, which is to discover these modes. And many of them were unexpected and came as a surprise. So we have essentially discovered three main modes. One which is the ordinary one, which we call L mode. Then came the H mode, which was discovered on the German machine called ASDEX, which has a confinement barrier at the edge of the plasma. And that improved the performance by at least a factor of 2. And then more recently, and this was done in JET, we discovered what we call the PEP mode, which is our jargon to describe that there was now a confinement barrier which was well in the core. And we also discovered that you could combine the two and benefit from both sides. And so we are further improving now on these concepts to make the best use of the magnetic field that we have.
What makes these patterns or modes of behavior in a plasma so important is that they can provide ways of slowing down the outward drift of particles and energy which limit the fusion process. In the ordinary mode, the heat and particles drift steadily towards the outside. In the so-called H mode, the drift is slowed quite significantly as the outer areas of the plasma are reached, keeping the energy in the plasma for longer. And in what is termed the PEP mode, there are zones within the plasma which slow down a migrant particle. This increases the energy confinement time and improves greatly the fusion performance. A reminder of the tiny quantities of fuel needed for fusion power came as samples were unloaded in preparation for the big run. This canister contains just a few grams of tritium. In a real power station, just 1 gram of deuterium and tritium as fuel would replace 10 million grams of coal or oil. Also, the daily waste from such a 1,000 megawatt plant would be just 2 kilograms of helium for a fusion plant, compared to some 30 million kilograms of carbon dioxide, sulfur dioxide, and other wastes from a fossil fuel plant. Humanity has shown that it can take on ambitious challenges if it feels they are worthwhile. The space program is an obvious example. But for only a fraction of the cost of the space program, huge strides forward could be made in developing practical fusion energy in a cause which may become critical in the second half of the 21st century.
We need a machine roughly twice the size of JET, or perhaps slightly more. And this is in order to achieve confinement times which allow the alpha particle to maintain the heat in the plasma. Such a machine would allow also, of course, to demonstrate fusion power production at the level of the gigawatt. At present, we are doing our research essentially one step at a time. We solve one question and then we process to the next. With a larger budget, we could essentially progress on 3 fronts. We could progress on the physics of what we call burning plasmas or ignited plasmas, which I already talked about. We could progress on material and technology. And a third aspect would be to research on concept improvement.
For fusion scientists, concept improvement means looking for new plasma modes, new ways in which a plasma might maintain fusion more effectively. This is an exciting prospect. There are also some key practical questions which an increase in scale will raise.
It's clear that one of the problems that future plasma experiments will have to face is that of the lifetime of the diverter. At present, the regime that looks more promising for the operation of the reactor, it produces large bursts of energy that land very fast on the diverter components. And now these bursts of energy produce very high heat loads. And if you were to scale these heat loads to larger tokamaks like a future reactor, that would produce very high levels of erosion and the diverter couldn't last very long. So it's clear that this is one of the challenges that JET, together with the fusion community, has to address now.
You need materials which don't contaminate the plasma, which can resist very high temperatures, and which can also resist a flux of neutrons. So these materials have been identified, they exist, but they need to be qualified in the real situation.
The dilemma at the heart of fusion research is that if fusion energy is to be available in 50 years' time, when it will be needed, decisions have to be made even while oil and gas are still plentiful. But the foundations for making a clear leap forward have been laid at JET, where systems for heating up the plasma to over 200 million degrees, for recycling the tritium fuel, and for maintaining a fusion plant remotely have provided a successful framework to test many of the other elements needed to enhance the fusion process.
At JET, basically, we've been able to show that fusion